The fastest spacecraft humans have ever seriously proposed would be destroyed not by a star, not by a black hole, and not by any exotic physics, but the ordinary dust floating in the emptiest space we know. Because at the speed required to reach another star, ordinary dust carries the energy of a nuclear weapon and arrives with no warning. That is not a metaphor. The engineers who designed breakthrough Starshot, the project that represents the most technically serious attempt humanity has ever made to reach another star system, calculated this. They ran the numbers on the interstellar medium, which appears on every diagram as a blank expanse between two labeled dots, and they found that the blank expanse was full. Not visibly full, not dramatically full, full in a way that only becomes lethal at the speed the mission requires, in a way that the diagrams cannot show, because the diagrams are drawn at the wrong scale to reveal it. The problem was not in the propulsion. The problem was not in the electronics. The problem was in what the probe would have to fly through. And what the probe would have to fly through has no solution anyone has published. That is worth holding for a moment. Not the absence of a funded solution, not the absence of a near-term solution, the absence of a published solution of any kind from any institution with any timeline attached. Imagine you are the fastest object humanity has ever sent anywhere. A probe the size of a postage stamp, several grams in mass, accelerated by a laser array on Earth powerful enough to push it to 20% of the speed of light. 20% of the speed of light means 60,000 kilometers every second, not per hour, per second. The distance between London and New York covered in 1/10 of a millisecond. The distance from Earth to the Moon covered in 6 seconds. At that speed, the probe would reach Alpha Centauri, our nearest neighboring star system, in roughly 20 years. That is within a human lifetime. That is the audacity of the project. Now, consider what 60,000 kilometers per second means for anything the probe encounters along the way. The space between stars is not empty. Astronomers have a name for the material that fills it, the interstellar medium. And on any distance scale humans are accustomed to, it is almost nothing, less than 1 atom per cubic centimeter in most regions. No astronaut floating in interstellar space would feel it, smell it, sense it in any way. At the speeds humanity has previously achieved in space, tens of kilometers per second for the fastest probes ever launched, it barely registers as a design consideration. The Voyager probes have been traveling through the interstellar medium for years and have not been destroyed by it. But the Voyager probes are moving at roughly 17 kilometers per second. The Starshot probe would be moving at 60,000. The medium did not change. Only the speed changed. What changes along with the speed is not arithmetic. It is not proportional. It compounds. When an object hits another object, the energy released at the collision point scales with the closing speed. Double the speed, and you do not double the energy, you quadruple it. Triple the speed, and you produce 9 times the energy. The relationship is not a straight line. It curves sharply upward. At the speeds humans have previously built spacecraft, a grain of sand in the path is a nuisance. It might scratch a surface. It might leave a microcrater on a solar panel. At 60,000 kilometers per second, a grain of sand the size of one you might find on a beach carries roughly the same energy as 43 tons of TNT, delivered to a contact point smaller than the tip of a pin. In the time it takes for a single nerve impulse to travel 1 millimeter inside a human body, in that same interval, the grain has already entered the spacecraft, converted itself and the surrounding hull material into superheated gas, and driven a jet of that gas clean through the structure on the other side. The probe does not have 43 tons of TNT of mass budget to play with. The entire design constraint of the mission is mass. A laser array on Earth, no matter how powerful, can only push a probe to 20% of the speed of light if that probe is extraordinarily light, the gram-scale engineering challenge that makes the project technically coherent in the first place. A probe that weighs grams cannot carry a shield that survives 43 tons of impact energy, and the interstellar medium will deliver that energy, statistically, more than once across 4 light-years of travel. The engineers did not miss this. In 2017, as the project's technical working groups were developing the mission architecture in detail, the Interstellar Medium Group produced an assessment of the dust threat that has been cited in every serious subsequent discussion of the project. The assessment was specific. Dust grain impacts at the mission's target speed represented the single greatest unresolved engineering threat to probe survival. Not one series of threats, the greatest one. The group concluded that no currently available or theorized shielding material provided a credible solution within the mass budget the mission required, and that dedicated materials research was necessary before mission architecture could be finalized. The assessment did not carry a projected timeline for resolution. It carried a flag placed in 2017 that remains in the same position today. The working group did not produce that flag carelessly. They had done the geometry first. The interstellar medium in the region between Earth and Alpha Centauri contains dust at a density of roughly 1 grain for every cubic kilometer of space. That sounds like nothing. A cubic kilometer is an enormous volume. Picture a cube with sides 1 kilometer long and fill it with air and drop 1 microscopic grain of material somewhere in that air. You could search that volume for years without finding it. But the probe is not searching. The probe is moving at 60,000 kilometers per second through that volume, and its cross-sectional area, even at postage stamp scale, sweeps through enough of those cubic kilometers over 4 light-years of travel to accumulate a statistical encounter rate of dozens to hundreds of impacting grains before it reaches its destination. Each of those encounters is an event. Each event above the threshold size destroys something critical. The probe's leading face is the first thing every particle sees. Whatever material covers that face absorbs the initial collision energy, vaporizes, and produces the plasma jet that either stays confined to the shield layer or punches through. The question of whether the shield layer survives is entirely a question of how much energy the material can absorb before it crosses the threshold between stopping the jet and transmitting it. Every known material has this threshold. It is set by the atomic structure of the material, the energy required to break the chemical and physical bonds holding the material's atoms together. At the collision energies the Starshot probe faces, even the hardest, most heat-resistant materials humanity manufactures sit comfortably below the threshold. They do not resist the jet, they become part of it. The obvious response is to add more material, thicken the shield, except that the front face will ablate, that it will lose material with each impact, and simply provide enough starting thickness that enough material remains after all expected impacts for the shield to still function by the time the probe arrives. This is how Whipple shields work on satellites in Earth orbit. A Whipple shield uses a thin outer bumper layer to vaporize an incoming fragment before it reaches the main hull, spreading the energy of the collision across a larger area where a thicker inner wall can absorb it. The ISS uses multi-layer versions of this approach and has survived millions of micrometeorite and orbital debris impacts. The concept is not exotic. It works. It works in Earth orbit because the velocities involved in low Earth orbit top out at roughly 15 kilometers per second for the worst-case collisions, and even at those speeds, the energy per impact is manageable with shield masses that are small fractions of the total spacecraft mass. A shield that absorbs a typical orbital debris impact might weigh a few kilograms and protect a structure weighing tons. The ratio is workable. At 60,000 kilometers per second, the same 1 milligram grain that a Whipple shield handles in orbit arrives with roughly 1.5 billion times more energy than it would in the worst orbital scenario. The shield mass required to absorb that energy is not a fraction of the spacecraft. It is not equal to the spacecraft. Under current materials physics, it exceeds the spacecraft's total allowable mass several times over. The shielded probe is too heavy for the laser array to accelerate to the required speed. A probe that cannot reach 20% of the speed of light does not reach Alpha Centauri in 20 years. It does not reach Alpha Centauri in a human lifetime. The mission requirement, the speed, is the same variable that makes the shield unaffordable, and there is no version of the mass budget where both coexist. Accept that for a moment. The shield that would save the probe cannot fly with the probe, because the probe must fly fast enough to need the shield. The second proposed mitigation is electromagnetic deflection. An electromagnetic field, or an electrostatic charge projected ahead of the spacecraft, can push charged particles out of the flight path before they make contact. Charged particles respond to magnetic fields in the same way a compass needle responds to a magnet. They deflect, following the field lines away from the craft. This is real physics, and it has been seriously studied as a radiation mitigation tool for crewed deep space missions, where the threat is charged particles from solar activity and cosmic rays. For Starshot scale, a magnetic deflector could be made small and light enough to be worth carrying. It does something useful. Against roughly half of the interstellar medium's particle threat, the ions and charged gas, it provides meaningful protection. Interstellar dust grains are not charged particles. They are neutral. A grain of silicate mineral or carbonaceous material floating in interstellar space carries no net electric charge, and a neutral object does not respond to a magnetic or electrostatic field. The field passes through it. The grain passes through the field. The collision happens anyway. The threat that the electromagnetic deflector cannot address is not a marginal fraction of the total threat. It is the structural threat, the high-mass impactors that carry the catastrophic energy levels. The charged particles the deflector handles would, at best, accumulate damage to electronics over time. The neutral dust grains, left undeflected, destroy the probe outright. The mitigation that works does not address the thing that kills. There is one remaining design response, and it is honest in a way that the other proposals are not. Design the probe as a sacrificial architecture. Accept that the shield will be consumed by impacts. Accept that the instrument core, the electronics, the sensors, the communication array, will survive inside a hardened inner capsule for only as long as the ablating outer layers continue to absorb the incoming energy. Do not design for probe survival. Design for core survival through statistical probability. Calculate the expected number of impacts. Estimate how many of those impacts the outer layers can absorb before the inner capsule is exposed. Hope that the inner capsule survives the first direct hit it takes after the outer layers are gone, and that whatever data has been collected by that point is enough to justify the mission. That is not an engineering solution. That is a probability statement dressed as a design philosophy. The probe is not expected to survive. It is expected to function until it does not. The question the mission cannot answer in advance is when the impact that penetrates the inner capsule occurs, which is determined by the distribution and size of the dust grains along a specific 4-light-year path that no instrument on Earth has ever mapped at the resolution required to predict individual grain encounters. You cannot survey the route. You cannot choose a cleaner path. You aim at Alpha Centauri, and you go. If the probe reaches the system, if the statistical outcome is favorable, if the dust grain distribution along that particular corridor happened to be sparse enough, it sends back a signal. That signal, traveling at the speed of light, takes 4 years to arrive. You are sitting on Earth more than 20 years after launch, and you receive a transmission from another star. Or you do not. 4 years pass, and no signal comes, and the probe was destroyed somewhere along the way, and you have no way of knowing where or when or what piece of ordinary dust was responsible. There are no other stars within range that do not require this speed. Any propulsion method that reaches Alpha Centauri in a human lifetime reaches the same velocity regime where the same physics takes over. A plasma drive, a nuclear pulse drive, a laser sail, whatever the propulsion source, the interstellar medium does not change. The dust density does not change. The energy scaling does not change. A civilization with better propulsion technology faces the same dust at the same closing speed if it wants to arrive at the same time. The medium is the constraint, and the medium spans every path between every star. Every serious, crewed interstellar mission concept that follows breakthrough Starshot in any technical roadmap will carry people through that same medium at comparable or higher speeds in a vessel large enough to house them for years, with a cross-sectional area orders of magnitude greater than a postage stamp. The statistical encounter rate for a crewed vessel scales with cross-section. A ship big enough for humans sweeps through enough interstellar volume every second to accumulate impact probabilities that no shield of any feasible mass survives across the required distance. The physics of crossing interstellar space at the speeds required to make it survivable for the people inside is the physics that makes the crossing unsurvivable for the hull around them. Kinetic energy scales with the square of velocity. That relationship is not a current-era technological limitation. It is geometry applied to mass and motion, and it does not change with better materials, better engineering, or more funding. The dust between stars does not care about the design review. It only cares about closing speed. Every proposed interstellar mission, from unmanned probes of breakthrough Starshot to the crewed generation ships discussed in long-term colonization literature, is moving toward the same calculation. The specific number varies with the design. The question is the same. What happens to this structure when the ordinary material filling the space between stars arrives at the surface of this craft with the energy of a weapon? And is there any mass budget on any conceivable mission that makes the answer something other than destruction? The calculation has been run. The flag is still there. The published solution is still missing.